All right, so let's continue. Last time we were talking about how to do the system of ODE. Okay, so for a system of ODE, we basically have two or more ODE putting together. And then we talk about the first model, which is predator and prey. We have rabbit and fox. We find that rabbit grow naturally and fox die naturally when you don't have food. And then they interact with each other by the fox capturing the rabbit, okay, which will slow the growth of the rabbit, which will also slow the decay of fox. Together, this is like the classic model for predator and prey. That's the necessity of why we need a system of ODEs. When you have more than one thing you're interested in, and they evolve together, okay? And then what we talk about is how to analyze a system like this. You can see everything we did in one dimension can now migrate to the two dimension directly. We have phase line before. Now we can talk about phase portrait. We have equilibriums before. We can still do equilibriums for the new thing. Okay. We can talk about it's a sink, it's a source. We can also talk about existence and uniqueness. Of solution. We can also talk about how to solve it analytically, which we know it's difficult. And finally, we can talk about how to do it numerically. So everything we did before, we're going to do exactly the same thing this time for the system. Okay, so that is the predator and prey model. Of course, we can modify it because we know in this model, we'll assume the exponential growth of the rabbits. You can actually modify it by changing this part into the logistic growth, which is more realistic. So predator-prey model, which we can simply just do dr over dt equals alpha r minus beta rf, and change it to if you want, you can also have a control problem here by doing harvest of rabbit, which means you're trying to harvest the rabbit while the fox is capturing them. So there are multiple ways of you can do this. Okay. We will talk about the details later. For now, just some examples. So that's the first reason we need a system of equation. When you have two things, rabbit and fox, you're interested in both. The second thing we need to talk a little bit is about how to solve second order or higher order ODE. And a classic one we had before is the spring mass system. Or we call a harmonic oscillator. Okay, if you still recall, it's MA equals F, or more precisely, y prime prime equals negative K over M. Why? Here M is the mass. And Y and K is the spring constant. And we can have third order derivative, fourth order derivative, and so on. Okay. In general, of course, you can solve it directly, but now we'll offer you an alternative way by doing this. By converting a high order ODE to a system of first order ODE. Let me show you how to do it. You start with this one. Okay? Now what you want to do is, you don't like this second derivative. Then what you can do is you can define a new variable. In this case, it's the velocity. You can call it y prime. Then beautifully, the whole thing becomes first order because y prime prime is nothing but v prime. So the second order change to first order if you just define the previous order derivative to be a new variable. Sounds good? The bad thing is you create a new variable. But then if you think about it, you already know how you define this new variable. You can put it here as a second equation. Now can you see that the original thing has two derivatives? Now you actually change them to be all first derivative by adding more variables for each derivative. But then you end up having more variables than before, but lower order of derivative. Okay, this is the equivalent system. Of this. Sounds good? Okay, so that's the second reason why we need differential equation systems, because if you have higher order thing, let's just give you another example. What if you have the third order? 6y equals cosine t. Well, it's third order, but now what I can do is I can define x equals y prime. Okay. I can define z equals x prime, which is y prime prime. And I can define r equals z prime, which is y prime prime prime. So every order of derivative become a new variable. First order, second order, and third order. The good news is becomes the original differential equation becomes, where is it? Actually, we don't need this one. Z prime, which is y prime prime prime, equals negative 2y prime prime minus 6y plus cosine t. But then we realize this is z. This is y. Okay. So you have a first order differential equation again. Of course, a side effect will be everything is first order. But you have a system instead. One for the first derivative, one for the second derivative, one for the third derivative. Okay, and you created these two by yourself. All right, so from now on, every time you see a higher order, you always have the possibility to change it to be a system. Then you are only handling first order. That's the second necessity of how to do this. Sounds good? All right, for systems, look for two cases. You have two things you are interested in, or you have higher order. That's it. Now let's talk about how to solve the system. The geometry of the systems. This is basically the equivalent section for slope field. Now let's talk about it with the example, the predator and the prey. Okay, the example we have is 2R, okay, minus 1.2 RF negative F plus delta RF. The first thing we want to talk about is called the direction field, which is very similar to the slope field we had before. Okay, now let's see. Let's take R equals 1, F equals 1, and plug it back into this right-hand side. What you have is dr over dt is 2 minus 1.2, which is 0.8. df over dt equals negative 1 plus 0.9, which is negative 0.1. Okay. That basically tells us if we put everything into the RF plane, we pick the point 1, 1. There is certainly a vector we can put here, which is given by 0.8, negative 0.1, according to our calculation. Sounds good? Okay. If I plug in R equals 2, F equals 2, what do you have? You have another vector. You can put that vector here. What if I put in a different R and F? Then you're going to have a different vector everywhere else. Still okay? From here, you can see you can easily generate a vector field. Okay. That vector field is given by F, XY, G, XY. We call this one the direction field. Of course, one thing we wonder is, this is easy to draw, but what does it mean? What kind of useful information does it give us? Well, now you need to think about, you basically for different RF, you know these two numbers. These two numbers is computed using the formula here. That's fine. But really, what you're talking about is these two numbers give you this and this. So the direction vector field is nothing but dr over dt, df over dt in our case. Or it's called r prime t and f prime t. Does it look like something similar in calculus 3, where you didn't use RF, you used x prime and y prime? What is that? Now, if you think about it, this one is actually the tangent tangent direction, tangent vector to the xy curve. That means if you have some parametric equation, which is called xt, yt, this vector x prime t, y prime t, basically give you the tangent vector at a certain point. Still okay? And moreover, this is actually the solution. So your tangent curve, you basically got the tangent direction for all the solutions by computing this vector field. That is why we need a direction field. Okay, that's the idea. Now let's take an example. Because we certainly want to draw it by coding. All right, so this is what we have for the predator and prey. Okay, alpha, beta, lambda, gamma, delta, and beta. I put everything here in the parameters that we just did. Okay. Now what we can do is we can let Python solve it. Okay. From here, you can see if we know how to solve it, we clearly see the rabbit population and the fox population. They actually grow periodically. Okay. When the rabbit is a lot, the fox start to grow really fast. But when the fox has a maximum population, the rabbit actually decay really fast because they basically eat a lot of rabbits. They capture a lot of them. That's once we solve it. But now, if we try to plot the direction field we just did, the red thing are the direction field. Let me just put it there by commenting out this and that. Okay. Sounds good? You can easily draw this. Okay. The key part is actually telling yourself, what does this mean? That means as time goes by, your R and F is going to change as a function of T. That means your rabbit and fox population is going to move. Okay? They are going to satisfy a certain kind of relationships. One is big, one is small, or maybe they both grow together. So either way, R and F, as time goes by, they draw a solution curve, which is how the population is going to change. And that is given by the blue curve. Still okay? And now the direction field tells you what? It tells you how are you supposed to trace this thing in order to find the solution of your thing. Just as the same way we try to trace this whole solution by Euler's method in one dimension. Still okay? And you should really pay attention here. That is, every single arrow here is tangent to this blue curve. That's the key of your direction field. So if you just trace the arrows, you'll be able to draw the solution curve in this way. Sounds good? All right. How to read the solution curve? Well, this is how you read it. Let's say you start from a point. The point is like 2.5. That's the initial rabbit and the fox. Still okay? As time goes by, you trace the arrow to the right. That means your rabbit population is going to grow. Meanwhile, your fox population is also going to grow. Slowly though. All the way up to here, which is the rightmost thing. That's where you reach the maximum rabbit population. Still okay here? From there, what do? You start to move up, but now move to the left. That means, yes, you have a maximum rabbit, but now you have a lot of fox. The fox is going to actually make your rabbit population decrease. Meanwhile, the fox itself still increase. Still make sense here? Until the fox reach the maximum, and they already killed a lot of rabbits. That means this is the best you can do. From now on, you won't have enough food. And you are going to decay. Make sense so far? And then you decay, and the rabbit decay with you. But because fox decay, the rabbit decay slowly because there's no more predators anymore. Okay. Until a point, the rabbit say, hey, now we have so few fox, we can start to grow again. We can grow back. And then periodically, this one just keep moving on this blue curve again, and again. So you have a very stable pattern of the two populations. Sounds good? And if you trace it, really, it's just solving the differential equation using your xt and yt and draw them as a vector field in calculus 3 by using the x and y direction. Together, you draw exactly something like this. That's the idea of direction field. Make sense so far? Okay, that also gives us a hint. If you want to do numerical method later, you just need to pick a point, calculate the direction field, move for this long, calculate the direction field again, move another step, just keep moving. You will be able to get the numerical solution as before. Okay, so it's not hard. Great. Second, by looking at this whole thing here, you observe two interesting things. The two green dots. Okay. Why? Because it seems like if you start from these two green dots, you don't move at all. Sounds good? That will be the same concept as in one dimension, which we call the equilibrium point. If you start from these two, you don't move. Okay? Second, if you look at the equilibrium point, look at this one in the middle. What's about this one? This one is pretty stable. If you just move away a little from there, you still actually circle around this point, right? But now if you look at this green, you will see something interesting because this green is not stable. If you move up a little bit, of course you will come back. So you're stable in the y direction or the f direction. Sounds good? However, if you just move a little bit away in the rabbit direction, you are going to just move away and never come back. So this one on this direction, the r direction, is a source. On the f direction, it's a sink. Okay, that's why the equilibrium in two dimensions is a little bit more complicated than before, because you have multiple directions now. Before there's only one direction. Sounds good? Okay, so that's what we have for drawing the direction field. By drawing that, you also start to see something interesting, that is the equilibrium. Share. So now let's talk about the equilibriums. Still the same system. Let me copy it. Okay, we draw the direction field using a computer. We see something like that. Which give us a solution. By picking a different initial condition, we have different solutions, which is fine. But then we realized there was a point here, right here, and there was a point right here. Okay. It doesn't move at all. We call them the equilibriums. Okay. How did you do it? Well, that's when things doesn't change. That must happen when dr over dt equals 0 and df over dt also equals 0. Therefore, you don't move. Therefore, you become equilibrium. So all we need to do is just set this to be 0, and set this to be 0. Let's go ahead and solve it, which is not too hard in this case. Let's take this first one. We can factor out r. This implies r equals 0, or f equals 2 over 1.2, which is 5 over 3. Okay. Set the second one to be 0. What we have is f negative 1 plus 0.9 r equals 0. This implies f equal to 0. Okay. Or r equal 1 over 0.9, which is 10 over 9. Plug it in and verify. You have two possible points. R, F equals 0, 0. That's one possibility. And R, F equals 10 over 9, 5 over 3. That's the second possibility. Okay, we just draw it. So it's not hard to see. This one is going to be the 1, 10 over 9, 5 over 3. And this is going to be the 1, which is 0, 0. Sounds good? Cool, that's all we got. Now, let me just write down the summary of this section. We use an example, of course. Now we want to write down the general thing. Okay. Number one, we should have a system. We use R and F, but in general, we should have dx over dt and dy over dt. Okay. Both of them should be a function of fxy and gxy. Note, there is no t. Therefore, we're doing something similar to autonomous system. Otherwise, the vector field won't be accurate. Then we focus on two things. The first one is called the direction field, which is given by fxy, gxy. But really, it's just x prime t and the y prime t, which is the tangent. Tangential vector. Which basically give you the velocity of your solution curve. Okay. Second, we have the equilibriums. Which is simple, can be solved by fty fxy equals 0, and the gxy equals 0. Sounds good. Let's see 3 examples. This time we are clear with the concept. We know how to draw this. We don't want to do it by hand, so let's do it with code. The key is not how to draw those kind of things. You use a code, you can really draw it. The key is try to understand and interpret those. Let's go back to the first one. Okay. We have a predator and a prey model. We set up the parameters. We draw the direction field. Then we were able to actually track all the direction field to get the points, which is the blue curve, which is the solution. We set both changing rate to be 0. We got 2 equilibriums. One is 0, 0. The other one is in the middle. Sounds good. So which solution are you going to get? It really depends on where is your initial condition. If your initial condition is here, you follow this blue curve. If your initial condition is inside, you follow a smaller cycle. If your initial condition is the equilibrium point, you stay there and never change. Still okay? And if initially you only have rabbits, no fox, that means your direction field should be the one, which is the x-axis. That means your rabbit just grows without limitation, following the arrow. It just goes to the right all the time. Still okay? You don't form a curve, you just grow. Similarly, initially, if you only have fox, no rabbit, that means you're on the y-axis. Still okay? That means the arrow points all the way down to 0. That means if you have no rabbit, only fox, the fox dies out. There's no cycle. As long as you have both, you start to follow a track, okay, which goes all the way as a circle. Does everything make sense here for the first example? All right, let's check the second one. What about the second one? Well, we want to do the modified predator and prey. Everything is the same. Everything is the same except the growth of the rabbit. Now has a limitation. It grows, but it never exceeds a capital N, which is the capacity of the environment. Sounds good? All right, so what's going to happen? Well, number 1, we should solve it. But number 2, we should really see the direction field. Here, I included 3 different solutions, each one starting from a different initial point, following the same vector field. Still okay here? Now, what do we observe? This time, no matter where you start, you will never have a nice dynamical periodic solution. Like sometimes fox is bigger, sometimes rabbit is bigger, and just keep going back and forth and back and forth and back and forth. You won't have that anymore. Sounds good? Instead, what do you have? No matter where you start, you got absorbed into one equilibrium, which stays here. Okay? That means your end population of your fox and rabbit, no matter how you start, will stay exactly the same. Okay, so several things break down. Number 1, if you think about there's only fox, no rabbits, the fox still dies out. Good so far? Okay. Number 2, if you only have rabbits, but no fox, according to what we had before, your rabbit just grows without limitation, so the bottom should have an arrow pointing to the right all the time. So you just grow to infinity. Now you can see it's not the case anymore. Why? Because if you look at the bottom, look at 2. On the left of 2, your rabbit increase. On the right of the two, your rabbit decrease. Why? Because you have logistic growth. Logistic growth has a horizontal asymptote, which is given by the n. In this case, is set to be 2. Therefore, of course, the rabbit will grow just all the way up to 2 and stay there. If you're above, you go back. Sounds good? Now, if you have rabbit and fox, the rabbit still have logistic growth. Then we have something similar to the harvest model we had before. Because the fox just eat rabbit, it's like harvesting. Okay? And harvesting will move your equilibrium to be a smaller number, but still, finally, your population of your rabbit stay constant. Okay. And because of that, the population of the fox also stay constant. Because if you're beyond that, you break the whole thing. Okay, then you will have less food, and then you die. Eventually, when you stop changing, you will be at the right stable population. Sounds good? Of course, the solution looks like this. Rabbit and fox, rabbit and fox, and rabbit and fox. You can see no matter how you start, the first time I start with 3.5 and 1. The second time I start with 3 and 2. The third time I start with reversed 0.3 and 3. But no matter what, the ending population of the blue and the ending population of the orange always stay the same, which is determined by the relationship between the coefficients. Sounds good? That's the second one. Later, if we want, we can calculate this. It's not hard to do. Now the third thing, harmonic oscillator. This is the second order differential equation. Okay. Now, like in your notes, we define a new variable, we call it V. We change it to be a system. Still okay? Now, like what we just did before, we can draw the direction field of the system. We can draw the solution curve. We can find the equilibriums, if any. Okay, how do we do that? Okay. This is the solution. We're already familiar with this. You have x and x prime. One is velocity, one is the displacement. They are sine cosine curves, right? So that's easy. The interesting part becomes x and v. This is the solution curve in the phase plane. How do you read it? Well, think about it. At first, you are at the very right end where you have the first, when you hold the whole spring mass system, you have a displacement, but you don't have velocity. Make sense so far? Now, starting from there, what's going to happen? Well, follow the arrow. The arrow tells you are going to go on this circle clockwise. That means your displacement is going to decrease, means the whole thing shake back. Meanwhile, your velocity went from 0 and start decreasing by going to the left. Still okay here? You reach the maximum velocity when your displacement is 0. After that, your displacement is going to come back, going to keep going, but your velocity is going to slow down. Still going to the left, but slowing down. All right? Until you shake to the leftmost, you have 0 velocity, but now you're at the very left point. You start to shake back. Still okay? That means your velocity become positive again because you're shaking back, even though you're still on the left of the relaxing point, but eventually you reach the maximum right velocity. And then just keep coming back and forth, back and forth, back and forth, and back and forth. That's how we read the solution curve in the phase plane. Sounds good? Do we have equilibrium? Yes, we do. Where is it? 0, 0. That means initially, if you just keep the mass to be there, the things stay there. There's no other equilibriums. That means no matter how you actually just to do the just right pulling, just right pushing, to make sure that after after a long time, the whole thing stay at equilibrium. It never happened. Nothing just keeps shaking. Sounds good? Okay. Now you need to ask yourself, what if I take into consideration of the friction, which is the damped harmonic oscillator? For that case, maybe it start to become possible that I can have some equilibriums other than 0, 0. Maybe. Okay. But this one definitely keeps shaking. So the only equilibrium is 0, 0. Sounds good? All right, that's what we have for the phase plane. We know how to read it now. Of course, to do some qualitative analysis, we did the first one. We can just do it quickly. All right, so let's see the example. First, the predator and the prey. Alpha R minus beta RF minus gamma F plus delta RF. Okay. Now we know the vector field look like this. Here's the equilibrium point. Here's the equilibrium point. Okay. To find the equilibrium point, we just need to set 1, 2 to be 0. So what we end up having is 2.00 and alpha over beta, that's your Fox, and your R is going to be gamma over delta. That's the rabbit. And that's the fox. Okay. A quick check should make sure that this thing makes sense. Okay. This will be the final population of the rabbits. So what do you know? Well, the bigger the gamma, the bigger the R. That means the faster the fox dies out, the bigger the final population of the rabbits. Okay. Think about delta. Delta is how much food is provided once you capture the rabbit. The smaller the food supply for catching the same rabbit, the faster the fox dies out. Okay. Therefore, the bigger the rabbit. So the whole thing here makes sense. Similarly to fox, a bigger the alpha, which means the faster the rabbit reproduce themselves, that means more food. That means the bigger the final fox population, because they have enough food to sustain themselves. Okay? That's how we read this. Case 2, modify the predator and prey, which is in the code. But if we write it down, we really just need to change alpha r, 1 minus r to the n, minus beta rf, negative gamma f, plus delta r f. Find the equilibrium. This is 0. Okay. Then some quick analysis. F times negative gamma plus delta r equals 0. This implies f equals 0 or r equals gamma over delta. The first one is r alpha, 1 minus r over n minus beta r equals 0. This implies r equals 0 or this one is 0. Now, if you think about the graph, two equilibriums. One is here, one is here. Everybody goes here. Okay. So clearly, the first one is going to be R, 0, 0. The second one is going to be the equilibrium where the R value is going to be the one we just calculated. So all we need to do is just take this one, set it to be 0, and then plug in R equals gamma delta. So F should equal alpha over beta, 1 minus gamma over delta n. Okay, so finally, the equilibrium here, we can give it a name, which is gamma over delta, alpha over beta, 1 minus gamma over delta n, corresponding to this one. Okay, the computation is pretty easy. Does it make sense? Well, the rabbits still stay the same way. The faster the fox dies, the bigger the final population of the rabbits. Okay, so it makes sense. This part is the same as before. So of course, the bigger the alpha, the faster the rabbit grows, the bigger the final population of the fox. Good. But now this one also tells you some additional information. The bigger the maximum capacity, which we can say the more grass we have, the more final population of the rabbits, the more final population of the fox. So you can see how the resource, how the grass of the rabbits affects the final population of the fox. Okay. Also, the smaller the gamma, the bigger the final population, which means the slower the fox dies, the bigger the final fox population. Make sense so far? Everything makes total sense, which should brought to your attention if you're careful enough. Strangely, before, when we don't have the equilibrium, we do have an unlimited growth of rabbits. The final population of the fox has nothing to do with gamma. Can you see that? It only has something to do with the rabbits. It doesn't matter how fast the fox dies. If you want an equilibrium, if you have unlimited growth. But in the second one, now how fast, which is gamma, how fast the fox dies does make a difference. From here, you can see another evidence that probably this model, once you add this term here, is way more realistic because how fast the fox dies should affect the final population of the fox, right? The average age of the fox, for example. Okay, it should affect it. Sounds good? Now the third thing. Y prime equals V. V prime equals negative K over M. Y. That's the harmonic oscillator. The face portrait looked like this. No, not this. I need to be careful. E. Like that. Okay. Y and the V. The first thing we observe is we only have one equilibrium, which is at 0, 0. I think that is pretty easy to see. You just set this to be 0 and this to be 0. You solve the system. You find 0, 0 is the only equilibrium. So that makes sense. Good. The second interesting thing, however, becomes super interesting. That is the solution curve in the phase plane. In this case, the YV plane, okay, is a ellipse. Because this one looks so nice. Still okay? That means what? That means y squared plus v squared is going to give you a circle. But now if you times a constant here, should equals 1. That's what we have for an ellipse. If a is 1, then you got exactly a circle. Let's not say 1, let's say r. Okay, just to make it look nicer. Okay. We will do the details next time, but now we just give you something which is very interesting. Sometimes it's really nice to study yt and the vt, which is in the original ty plane, but the graph will make look really not nice. On the other hand, sometimes you can solve the whole thing in the phase plane. which is the y as a function of v. By doing this transformation at a different level, sometimes you have something really nice to analyze compared to the original YT thing. It's just the final result is a little bit harder to interpret. Okay, but solving it becomes super easy. And later, in physics especially, you will see people exploiting this kind of convenience again, and again. Okay, so that is solving the differential equation in the phase plane. We will touch a little bit next time for this. All right, that's all for today.